I hope you're able to see the screen.
Yes, very well.
Thank you very much. So, um, the thing is about the main thing that we are concerned here in the Result Center and also with these environments is that we um, consider dynamic optimization problems as in contrast to the static optimization problems. So in the real world, we often observe, as we have seen in the talk before, that there's a lot of change. There is a rolling planning horizon, new customers, new information arrives into the system randomly. Sometimes there's some change to information that you already have. So these need to be considered in order to apply certain problems to the real world. And this takes us from the point from stochastic optimization to dynamic optimization. So we had some applications in the industry, and there we considered the problem as a stochastic optimization problem, and we basically pursued a re-optimization approach. So whenever there was a change, we re-optimized. Respectively, we found out that there was a lot of changes. And there is also, you cannot always expect that the solution that you propose is executed as proposed. And so basically we went with a fixed interval in which we re-optimized and attempted to accommodate all the information that we have. Also because in the real world you have different systems that are interacting. And so in general, what is really important is that the world and the optimization problem becomes much harder if we go from the static case, which we know how to solve well. We can describe them in linear programs, mixed integer programs, heuristic algorithms are used to solve them. So they're just quite well researched. But in dynamic optimization, it's very difficult. We have this state space, we have some actions that we can recommend, there's some kind of exogenous information, and there is you can make little steps in a dynamic optimization problems that would be considered maybe good from the point of a certain cost function, but in the end it leads the system towards a state which is undesirable. And that is something you want to avoid. So you can make some optimizations, but in the end, maybe you're, with respect to a certain cost function, you're targeting a system state where it is the buffer is full and you cannot do anything anymore. So that's something that you have to avoid. So you have to consider cost functions very carefully on what you do. And the main difference from an algorithmic point from a static optimization problem is that you intend to find a solution, which is described usually as a vector of decision variables. In the dynamic optimization problem, actually you have a function that you seek. An optimal function is also called policy that optimizes this problem. So the space of potential functions is much larger than the space of optimal solutions that you can find. So it's very hard challenge, but we feel that it is very necessary to consider this in these changing environments, in these practical applications. So some motivation also why we do this. As I said, we have them occurring in practice very often. We see that we have rolling planning horizons and the plans becoming infeasible long before the planning horizon ends. And still, then the question would be, why do you consider such a long planning horizon? Of course, you're making changes. You're suggesting actions now which have an impact that is much further along the line. So if I put a certain block, a certain steel slab, whatever the real block is, to a certain place, then this affects maybe in 2 hours when I need to retrieve it again, it affects the situation there. So I need to consider longer planning horizons, even though knowing that the solution will change long before this planning horizon ends. And yeah, the second thing, of course, the challenging, so it's a kind of a research challenge because these are very hard problems. How do we solve them? And overall, we think, and that's why we also created the Joseph Ressel Center, or let's say proposed the Joseph Ressel Center, is that we feel that there is a lot less research with respect to dynamic optimization problems. There is a lack of benchmark problems. There are some benchmark problems that are used and widely cited, but we feel they are very simplistic. They are lacking, for instance, some properties where you just try to follow an optimum, but your actions that you actually propose are not really influencing the system. So this is called the time linkage effect. When you're making an action, the course of the system changes. That's something that is not present in some of the benchmark problems. And also we think that interesting instances are hard to obtain. So we consider this is not a methodological research here, what we're doing. We're not inventing in this specific research a new algorithm or so. That was presented in the last talk by my colleague. In this talk, we want to focus on the problem, research on the problem themselves. What is appropriate problem? What are the parameters of this problem? But why they are challenging, and what we're going to do with them. We think that this is very important for the dynamic optimization problem point of view, because there are so few and because they are not so well understood, and because they have so many parameters that they are also much harder to determine and to define. Okay, so I have already noted some challenges. Just reiterate a little bit. We have, especially as you already saw before, the asynchronous operations. So you have the dynamic environments that are going out of sync. You have the optimizer and the decision. This is very important and is very realistic to consider. And the second thing is the incomplete and uncertain information that you can have. So you need to learn about the uncertainties of the environment. You cannot really assume something is true and will stay true forever. It can be that there is new stuff coming, and you cannot really change maybe your model, but maybe you need to adapt to whatever the new stuff is doing. Maybe it is a little bit slower. Maybe it will learn over time, become faster. So some of the variables need to be learned while the system is being solved. Okay, coming to the dynamic environments that we have created so far in this project. And our goal here is to take the real industrial environments and put them into a more abstract and more in a form that we can communicate easily to the scientific community. So this is kind of the goal here. Take the real industrial environment, simplify it, abstract it, but still maintain the challenges that are there, and then create a dynamic environment, implement it, and provide it to the research community for methodological research. The first environment that I want to talk about is a hot storage, what we call its industrial pendant is a continuous caster that is a continuous casting process that delivers steel slabs, and these have to be stored in a facility and need to be retrieved at some point. Here we have an arrival stack where new blocks appear at the bottom, and a handover stack that is available. So that's kind of a transport that is available, and a crane that moves from the arrival stack here to the handover stack. So that's a very simple model. Still, the real model is more complex with more cranes and more handovers and different types of handovers, and of course the properties of these blocks are in the real world much more complex, with even including a temperature and such. So this is not included in this model. It's still kept quite simple. But still, you have these challenges of asynchronicity, you have this challenge of incomplete information, so the block eventually gets this blue check mark, and at this point in time it can be moved to this handover before it cannot be moved to the handover, or respectively will not be transported. And you have this due date, so this is kind of the time here that is ticking, and you have to move it to the handover before the due date, but only after it gets this blue check mark. And you don't know when is the ready date, so to say, when does it get this blue mark. And you have to, still there's some kind of correlation with the due date, so you can use this information in stacking. But you see here, this one, you have to remove a lot of blocks. You can only remove them one at a time. And this is very, very hard. So overall, The challenge here is to deal with uncertain and incomplete information in this case, but we noted that this environment, due to the simplicity and the grain just moving one item and so, is still rather easy to solve. So it's not that complex in this abstraction. There you can derive handcrafted rules, and these will be able to perform quite well. We think that of course, it's a challenge to perform even better using more elaborate models, but this is still not so difficult. So it's kind of an entry point. Then we have this Coil Warehouse scenario that my colleague Johannes Kader talked about in the previous talk. He was using this environment for the research. Again, this is the challenge here is we have a much wider range of buffers, and supposedly there will be more arrival stacks and handover stacks, and I hope the network is okay. It says bad network quality. So we have more cranes and interaction between cranes. Actually, that's the main challenge here, to consider the interaction between the cranes. This warehouse this environment is currently under research, and we are seeing that with some kind of look-ahead policies, which as Johannes has described, optimizing, taking a genetic algorithm, taking a look-ahead policy and solving this with respect to a certain planning horizon, then implementing the next decisions, is a good way to solve these environments, at least from the scheduling point of view. And we have a third environment, which is we call the rolling mill, and this presents a complex stacking problem similar to what we had before in the first environment, but also the interaction between cranes, because we have two cranes and not all the cranes can reach all of the positions, and there is some batching needed. So the cranes do not transport one block at a time, but they transport multiple blocks, and you have to transport multiple blocks in order to service the handover places in time. So that's very important here. And this challenge is very complex, and it has not yet been solved. So this dynamic environment has not yet been solved satisfactorily. We don't have yet a solution for this yet in this abstracted and simple form. So it's a very difficult and very tough problem. Again, a second thing, why is the parameterization so important? You have to consider, if I go back here, you have to define some kind of arrival process that will create new blocks into the system, and you have to create some kind of departure process for this blocks to disappear, and some kind of ordering that is required. So you have to determine, of course, in this environment, all of the numbers that you can see here. So the block ID is trivial, of course, but the sequence in which they should be removed and so on. And this is something that the dynamic environment needs to decide and needs to parameterize. And there are a lot of course of parameters for these kind of things, and stochastic distributions that you have to take into account. So just a quick example of how we're doing it in the hot storage case. We're using information from Little's law and basically queuing theory and determining some of the parameters. For instance, we take what kind of scenario do we want to consider? Do we want to consider the grain taking a lot of time? Do we want to consider the grain having a more relaxed atmosphere? These create different challenges for different solvers. So that's something we want to control. So we set, let's say, a utilization for this grain of 60%. Then we determine what could be the processing rate of this crane by taking into account how fast it moves, how fast it can move, can relocate the blocks, and determine how many blocks, for instance, could be relocated, let's say 10 blocks at a time. From these equations, we calculate the arrival rate that would lead to this kind of utilization. And then also we determine on a second level, what is the number of blocks I want to have in the system, because the crane is having a much harder time with many more blocks. So as you can see here, if you have multiple blocks, then their stacking problem becomes much harder, and thus this also influences. So we put, according to Little's law, the number of blocks that we want in the system, calculate the mean duration, and use that as a kind of prescribing the blocks to stay in this time, kind of sample the due date from this information. So that's something that you have to consider when you parameterize these models, when you create instances, dynamic optimization problem instances. It's much more complex. You need to work with queuing theory, and this is still a very simple approximation. Okay, so this is not a very elaborate, and you can not really calculate this exactly. So that's a challenge. We implemented the models. I'm coming to the end soon, and put them on GitHub. So they are open source available. There are simulations as well as some starter kits. We used a simple simulation kernel written in C#, which is running in pseudo real time, and they're all standard interfaces. So we have protocol buffers for describing the messages. We have CRMQ for the transport. So these libraries are available for a large range of programming languages. So you're not limited with respect to the solver that you implement. You can use almost any programming language that you want to use in order to optimize this kind of dynamic environments. And they were very easy to start also. So we try to make this really simple and easy so that it's accessible and that people can use it. And then we run a competition. The first competition was launched in another conference that has these competitions, and we have increased participation in these competitions. We note that this is very well received, and also we submitted it to the next year competition. And there we have a website even where you can register, where you can start and launch the simulations and environments, and where you can communicate your solutions to the environment via this website, and this is used then to rank the participants. So we feel that that we hit the nerve, and that we're getting more responses, and that is also the final message here. Please, if you're interested in this, consider to take part. Thank you very much.
Thank you so much.